Everyone, this is John Buck back with another array signal processing video. In this video, we're going to just talk about the beam pattern for narrowband signals, or beamformers for narrowband signals. And the basic idea here is the beamformer in array signal processing plays the same role as a frequency response in our classic time domain signal processing. The beamformer tells us what the gain is that a given set of array weights will create for plane waves from a certain direction, just as the frequency response told us what the gain that a given impulse response would create for complex exponentials of a given frequency. So we'll talk more about that analogy as the term goes on, but it's the basic idea for a given spatial filter, what's the gain that it applies to plane waves from each different direction. All right, so let's switch over to the whiteboard and we can pick up on our earlier time domain beamforming story and continue it here with narrowband. So picking up where we left off with the time domain story, we said that our beamformer, oops, missing an N here. Right, our beamformer output as a time signal would be the sum across the array where we're going to take each sensor, the signal measured at each sensor, f sub n, and we're going to shift it to the left. We're going to advance it by some delta of n of theta naught, which is the time domain shift we'd expect for a given look direction, so that if signals are coming from the theta naught direction, they'll all be lined up, right? So these are the shifts that undo the delays for a plane wave coming from the theta naught direction. And after we do that, we may also be applying some gain to each of them, right, and combining those together. So moving to the narrowband case, we're going to say, well, what if the signal coming in only has one frequency we care about, right? There's one value of omega. It would be simpler to think of this in the frequency domain. So let's take the Fourier transform of this equation. And when we do that, we're using the linearity of the Fourier transform, right, that we can recognize that these sums are taking the scaling and the sums just carry through to frequency. We get the Fourier transform of the nth signal that we receive, and then we also get the phase shift, e to the j omega delta n of theta naught, right? So we have the phase shift for the nth sensor that way. So, and omega is the narrowband frequency of interest. So we're going to move the g to the n and e together. We say that combination of gain and phase we're going to think of as a complex number. That's what we call the complex array weight. And at the same time, we saw in the video on replica vectors and earlier that we know f of n, these fn of omegas are just different delayed versions of the same signal, and that the replica vector captures that. So we can do a bunch of stuff here together to simplify this sum. Let me do the first step of collecting the array weight. Right, so when we do this, we get the these terms here all together, the gains and the phases that are being applied to the sensors, we consider the complex array weight. So we'll call those W sub n conjugate. And at first glance, when you first see this, we say, well, why a conjugate? And there's a reason for that we'll see later. I remember when I first saw this, it felt weird to call it W conjugate, but there are good reasons we'll see as we go on. And then on the other side, we could say, well, if the signal coming in is actually a plane wave, we can write the T of n's out more simply using the expression we had for T of n, remember? Or I'm sorry, rather tau of n. Right, so when the incoming signal is a plane wave, which is when we're looking at beam patterns, what we're focusing on is the idea of we think about one plane wave at a time, or one angle at a time, the way we think about one frequency at a time in the time domain. Right, so we can use this, and when we do that, we recognize that that this being linear, we can use the replica vectors we saw in the previous video to simplify or to represent sort of this whole f as a vector. And so we make some simplifications. But first, let me drag stuff up to make a little more room here. So we can simplify all this, all the dependence of the phases here in this elements of v sub n here. Where again, v sub n is the replica vector we saw on the previous page, and this f of omega has pulled out front. So we basically say the output of the beamformer at this frequency will be the propagating signals at this frequency, plus this gain that has to do with the array weights and the replica vector. And again, let me write out the Bn first. And actually, as I do that, I should make clear that the Wn's depend on theta naught, so I should keep that in there, the look direction. They depend on the look direction, theta naught. And the Vn's in this version depend on the direction of the plane wave of interest, theta. So let me fix my note. And then now I'll write out, again, remind us what the elements are. Right, so the array weights for the theta naught direction are the gains we're picking g sub n and e to the minus j omega times the delta of n theta naught, where again this is minus, so that when I take the conjugate here, I get the positive exponent I want to compensate for these. And the v sub n, the replica vectors for theta, have this e to the minus j omega d over c times nc minus n cos theta naught. Right, and so these are our things, and when we think of them these ways, the w sub n and v sub n can be thought of as the elements of a vector. And if I'm multiplying two vectors element by element and then summing, that's an inner or dot product, with a little additional wrinkle, though not a big deal, that we need to think about the dot product in the spatial frequency, in the complex domain. We're thinking about complex numbers. And so when we take the transpose, we also take conjugates. And so let's make some space and then bring that notation in. Okay, so again, where I've put W underbar and V underbar to remind us these are vectors, and this H here means conjugate transpose. It's called the Hermitian operator, so it's like the normal transpose where you flip the rows and columns, or in this case, it's just a vector, so it's turning a column vector into a row vector, but we take the conjugate while we do that. I'm going to pan up a little bit more to make room, and then we'll write up the W vector and the V vector as column vectors, since this is the first time we're seeing them. And for now, I'm also being careful to keep the omega naught, or sorry, the theta naught and theta there. As the semester goes on and we get familiar with them, we'll recognize those are often implicit, that replica vectors are functions sometimes of theta. Sometimes we'll do them in terms of kz, that is the wave number projected on the array axis. And sometimes we'll do them just in terms of the directional cosine, u equals cos theta. Depending on the problem, there are advantages to doing them in different ways. And we'll see, there's a place of engineering judgment of which variable for angle is the best in a given problem. So assuming that the deltas were based on a plane wave propagation, when we plug in, we have this vector going from n equals 0 down to n, and I should again have reminded us that nc, right, is the index of the center element, assuming we have an odd number of elements in our array, like we saw when we talked about plane waves. So this is, nc is n minus 1 over 2. But this vector is just stepping along, where the only thing we're changing possibly the gains in front, and counting through these each time, where this is sort of nc minus little n, so as n goes from 0 down, and at the middle element, they cancel out, and I have e to the 0, so I just have the gain for this one, and then the exponent changes sign and goes up the other way. So this is my weight vector, assuming I have a plane wave coming across my uniform line array with n minus 1 sensors. Similarly, we saw the replica vector on the last video, so I'll just write that here next to it. I had to erase a little bit of the conjugate transpose here to make room, but here's my replica vector. And we see, not accidentally, they have very similar structure, right? That they have very similar exponents here. The difference is whether the theta naught for the look direction versus the theta the plane wave is coming from might be different. And that I also possibly have these gains out in front, that I might put different gains on different sensors. And we'll see in an example, the simplest thing is to average them to make all those gains the same. But we'll see later in the semester, we'll look at array shading and tapers that might do something different. Okay, so this is we've got our array weights and our replica vector. And since this thing up here comes up often enough, this inner product of the two, we call that's actually called the beam pattern. The inner product between a given set of array weights and the replica vectors evaluated as a function of theta, right? So the W's are fixed and V is varying for the beam pattern. So let me start on a new page and we can write that down. Right, so if we pull this out again, we have this inner product between the array weights, which is the W Hermitian, and the replica vector theta. We can think of this as this is the beam pattern, B of theta, which is also parameterized by the array weight. So again, W is held fixed. We're looking at this as a function of theta, and this is the beam pattern tells us the gain that these weights W make for a plane wave coming from direction theta. We may also, at other times, we'll look at the beam pattern as, we may have beam pattern as a function of kz or of u, k sub z for the wave number, or the directional cosine u. But let me write this out first. And again, reiterating, the beam pattern is the gain that an array weight vector W applies to a plane wave arriving from angle theta. So in that sense, it's a spatial analog of the frequency response, right? Because W here is fixed and we're varying theta. We're looking at all different input eigenfunctions, the plane wave eigenfunctions we saw a few videos ago. And so the same way that a frequency response says, well, for a fixed set of impulse response, right? For a fixed filter impulse response H, it tells us the gain that H applies to complex exponentials of different frequencies. So that's a place where we're going to start and keep building on our analogies to time domain processing, because for narrowband signals, these things are, the narrowband spatial processing has a lot of strong analogs to classic time domain processing. Another thing I should mention in sort of closing comments here as we wrap up, the beam pattern is a function of frequency, right? So I haven't written it there because we're assuming narrowband frequency. We're only working at one signal. But if I go back a page, right, all of these, both W and V, both the weight vector and the replica vectors have omegas hidden in them as well as the thetas, right? So for a given W, these phases would be different, as would V's. And another comment worth making is, although we're thinking about this in the terms of the uniform line arrays, it has much broader applications, right? You can still have beam patterns to think about more than multi-dimensional arrays, 2 or 3-dimensional arrays. You don't have to have uniform line arrays for these. And it doesn't have to be simple plane wave beamforming. For other beamformers, we'll see, we still want to know other sets of array weights. We've come up with other ways. We'll still want to know, well, how do they process plane waves? Because those are still the fundamental building blocks, the eigenfunctions of propagating in free space in the far field. Okay, so I'm going to stop this video here. The next video, we'll look at an example of computing a beam pattern.